So we have an innovator, entrepreneur, and enabler of innovation rather than just a passive innovator. Durell Hammond from Pyrocal will talk to us about carbonization, a sustainable technology for circular economies. Over to you.
Thank you very much. I've got a slightly different presentation to offer today. I'm going to show you a video that I have that sort of came out of the discussions yesterday. I thought it was relevant to show it to this audience to understand where the nutrients in the circular economy kind of start and the commitment required to deliver that nutrient to people in population centres like Sydney. So the business I run, my business is effectively agriculture, producing fresh vegetables, perishable, every day of the year, delivered to Adelaide, Melbourne, Sydney, North Queensland, Canberra, and also some cotton production to the west. So we have to manage all sorts of resources. This first video just shows you a little bit about the commitment that's required to deliver the nutrient in the first place. And I think the challenge that we've all got in this whole Nice Hub project is to find commitment to return it. So I just want to show you the commitment that's required to deliver it in the first place. This is in Gatton, in Lockyer Valley, where Christine is from yesterday, during the flooding last year. That's sweet corn. These guys are harvesting lettuce. You're all aware how much lettuce cost at some stage through the year last year. We didn't cause that. The supermarkets caused it. You know, this enterprise has lost a considerable amount of money over the last 12 months. So it's demonstrating resilience, commitment, and all of these people deliver it. And you can see what we had to deal with. And you can appreciate the consequence of all of this. You know, we hate doing this to soil. It's just not right, but it's what happens. And this occurred, we had two events like this, as the first slide said. We had two rain events last year. One lasted 40 days, one lasted 60 days, and delivered us way too much rain. Throughout all of this, the supermarkets imposed all the usual quality control measures on us in terms of dirt, insect, you name it. Absolutely no care, no empathy, no understanding as to what was required to get fresh produce to market. Everyone wants a lettuce every day of the year. They want strawberries every day of the year. And this is a consequence of that demand. So that kind of helps set the scene. Behind it people could still smile, and get the job done. And when we prepared this video, which was a collection of material from all of those people's mobile phones, as you could see, it wasn't a staged production. We put it together and got the group together last November and showed it to them. They all cried. There's about 800 people. So that's the sort of commitment that we've got to work towards to get nutrients back. We just can't say, oh, it's too hard. We've got to grind on. So that's the challenge, I guess, for all of us, as we sort of sit here and share ideas. And I don't know what I'm doing here. How do I get that full size? Sorry. So now back on the topic, but I think that helps set the scene. So thank you for sitting through that. In terms of carbon, or the topic, carbon removal enabled. This is a 10-year project from my point of view. I started this in 2013 and it's on the back of nutrient recycling. So we have about 100,000 tonnes of feedlot manure as a resource on a feedlot in the Southern Darling Downs in Queensland. And I looked at that as a resource both in nutrient terms and energy terms, and looked at trying to create an energy pathway. At that point in time, energy was more important than nutrient. This is 10 years ago. I dug out some research that was conducted by, or funded by MLA, Meat and Livestock Australia, which is not unlike the NEAS Hub project, very, very similar. And looked at anaerobic digestion, looked at combustion, gasification as ways to extract energy from that feedlot manure and turn it into a form of energy that we could use. Couldn't get it to stack up in any way, shape or form. The conversion of thermal energy to electrical energy at best is about 30%, with a well-organised coal-fired power plant. When you go to small waste to energy sort of systems, it gets down around 17%. So we're losing 83% of the available energy gets lost in the transformation from thermal energy to electrical energy. And that just didn't work for me. So we ended up going down the nutrition pathway, and with that feedlot manure resource actually developed a business composting, granulating the manure, value adding it with gypsum and other materials, and that business is now well and truly up and running. But throughout that journey, I couldn't let go of the idea of gasification and treating biomass that didn't have a better home at that point in time, remembering this is 10 years ago. So we'll go through that sort of journey, and then the market shift in 10 years, we're all aware of, that the carbon economy has emerged, and we'll see that throughout this presentation. So behind the business, obviously, are people, and 90% of those people have been with us since day one, so they're committed. We're all very committed to this. We've invested a lot of money, a lot of our life in the pursuit of this sort of betterment. So we design, build and operate equipment. We do it in Australia, and we have invested very heavily in R&D. Historically, as I said, we formed about 10 years ago, and that work commenced in Vietnam, as it turns out. But in what? How do I press the wrong button here? I'm sorry. So the boys did this little animation. I've got to play it. So we are now in a circular carbon economy. And in agriculture, we talk about nutrient. There are three elements or things in a plant production system that aren't classified as nutrients but are absolutely critical to plant production, and they are water in the soil, oxygen in the soil, and carbon. So I include carbon essentially as a macronutrient. It's certainly an enabler for a lot of the nutrient cycling systems that occur in the soil, in the living soil. So very, very important to us in all its forms, whether it's labile carbon, non-labile carbon, recalcitrant carbon, very important to us. Because we have an international footprint and have done some social impact enterprises overseas, we do subscribe to the United Nations Sustainability Goals. They're very important to us. In terms of our technology, that's kind of where we've landed. That system is 2 years old, but it's already been superseded. It's still in operation. That's based at Wellcamp in Toowoomba, and it is processing nutshells 24 hours a day that comes from a pecan macadamia processing facility in town, and we're producing a high quality carbon that can be a precursor for activated carbon. In terms of our process, again, I've got to explain what's happening here. We operate an updraft rotary gasifier. So on the left you can see material entering a rotary hearth. That hearth is typically up to 2 metres in diameter and about 2 metres high. The residence time for the material as a continuous process is about 100 seconds. The material flow rate into that particular machine is about 650 kilos an hour, so a bit over 10 kilos a minute, continuous operation. And in this we have four chambers, 4 discrete chambers effectively. Material passes through slots from top deck to this deck to the 3rd deck and then out of the machine. We call this the drying zone, so the material is entering at up to 20% moisture. We've obviously got to get rid of that moisture before we can successfully carbonise. Then we have an oxygen limited area here, which we call the pyrolysis zone. It's not oxygen deprived. It has some oxygen, but it is oxygen deprived. It still contains oxygen, unlike some pyrolysis processes that have zero oxygen and they use inert gases. We have some oxygen there, and we need that to maintain gas flow. And as the volatiles are burned off, they're coming out here as an off gas, and the leftover material descends and eventually discharges at around about 25% of the inbound mass. So 75% of the mass off gas, 25% fixed carbon, or depending on the feedstock, other elements. We then go into a thermal oxidizer where we add more air, burn out those gases, and the simplicity in our design is the close coupling of the thermal oxidizer to the rotary hearth, so that we don't have a dangerous gas zone. Lots of hazards around trying to deal with syngas, and not everybody's up to dealing with those hazards. We introduce urea at that point if NOx is a problem, and we have SEMS, continuous monitoring, at the stack, so it gives a signal that feeds the urea supply if NOx is an issue. When those gases are burnt out, which typically takes about 2 seconds, and we've got temperatures in there up just over 1,000 degrees, so we've got good conditions for destruction of POPs and volatiles that exist inside the gas flow. We then collect the heat through a thermal heat exchanger, and it goes off to whatever process condition it can offer. In the case of the Logan wastewater treatment plant, it's providing hot air for a drying process. Within it are a wet scrubber, Venturi scrubber, dosed with magnesium hydroxide if SOx is an issue. And then depart to stack. In our trial unit, we also have a wet ESP in there to deal with any PM 2.5 that might be problematic. One of our very early projects was to Haiti. We were successful with a social impact enterprise funded by Shell, MIT, the US aid fund also put some money into this, put a gas processing facility into cooking charcoal into Haiti. That addressed a number of social issues and environmental issues. You know, had rainforest deforestation, women in the workplace, and just finding fuel for themselves. Unfortunately, that whole plant was just blown away in a series of hurricanes. It no longer exists. But just an example of how versatile this particular gasification process is. We can deal with this at the bottom end, so they had no power there. We fueled it with 12-volt batteries and solar. We did a number of projects in Vietnam, 2015 to 14 to sort of 16. Again, looking to just better utilise rice hull in their brick kilning industry. That survived for 2 years, and then a successive 5-year plan from the Vietnamese government stopped them harvesting clay from the Mekong Delta to make house bricks. So the clay bricks were replaced by Besser blocks, basically. So that whole business model collapsed. And then all the way through to the biosolids gasification facility at Logan. So you can see that throughout history, that even now we can move all the way from a utility quality process to a true third world process, which is why I really like the technology. Joanna's going to talk a lot about this later this afternoon, so I won't dwell on that at the moment. In terms of the biochar as an output product, we're all aware that the many possible uses for biochar, and we've just got to figure out a good way to use them now, and our research is focused on the application and operability of using that material. 2 years ago, voluntary carbon trading markets established for engineered carbon, and this changed our business case enormously. So we're all aware about the sequestration, the permanence of biochar in a carbon economy. So they now have a number of volunteer markets operating, and that's the sort of magnitude of value that's apparent at the moment, from 2 billion to 40 billion, and it's happening. So that's great, because that's going to fund these opportunities. So there are some leading standards. We've actually set ourselves up with Puro Earth, which is the NASDAQ business. And the output from that for us, given our process, so we've got a very clean process as opposed to some of the kiln-operated biochar processes that operate in most of the equatorial zones around the world. We're producing high-quality carbon with a small environmental footprint. So life cycle analysis now for Puro is cradle to grave. Biomass right through to where it's actually hits the soil, if it's going into a soil system. So it counts for transport, all sorts of things along the way. But the value proposition is significant. So bottom line is each tonne of biochar that we produce using our method with the quality of feedstock that we're using, raises something like $700 per tonne for char. And the objective of that carbon trading market is to fund investment in the production of more recalcitrant carbon. It's not meant to just disappear in profits. The idea is to reinvest. So they have this really important aspect in their assessment of it, which is called additionality. So if there's another reason that biochar has been produced, such as a regulation, you're disqualified from trading carbon in the carbon market because there's a preceding regulation that ensures that that process has to occur. So that's a term called additionality. So you have to demonstrate additionality. It won't last forever, clearly. Rules change, so but that's funding growth. In terms of research for ourselves, we do our own in-house applied research. We have a couple of people that qualified in agronomy and environmental geochemistry, and they're looking at alternatives to non-sustainable practices like the use of peat moss in seed raising mixtures. In our vegetable business, we use a lot of transplants, and they're all grown by an external business. If we can use biochar in that seed raising mixture instead of peat, that biochar finds its way into the farming system. And broccoli transplants, for example, we're putting in 40,000 a hectare. If we use 10 grams of biochar per seedling, do the maths on that, 3 crops a year. I'm not going to do the maths for you. You end up with a significant amount of biochar in the soil without any real operational effort, and with some real benefits, particularly in terms of sustainability around the harvesting of peat moss. We're looking at negative priming of biochar. We're doing some work with CSIRO and cotton on that, looking at recycling cotton clothing back into soil, and looking at the degradation of that fibre in a soil system with and without biochar. The degradation slowed down significantly in the biochar treatment, which tells us that there's something going on there with the carbon recycling that is beneficial in terms of raising soil organic carbon levels. Enhanced efficiency fertiliser is another key area of focus for us at the moment, and I'd like people in this room to really give that some thought. What we might do about using a material like biochar to enhance the efficiency of the fertilisers we currently use. If you take nitrogen at the moment, if we consider in a soil system that our nitrogen use efficiency is under 50%, we're already compensating for known losses by over-applying nitrogen by an order of magnitude of 2 times. That's significant. So we need to find ways to change that, and biochar is one way of doing it in a non-chemical system. There's chemical treatments that may help, like polyvinyl acetate coatings, urease inhibitors, nitrification inhibitors, which are biocides. I'm not particularly sure about where we want to go with them, but I think that's, for me, that's an area of particular focus. We do our own leaching studies in-house. USQ do a lot of them for us as well under this NIS Hub project arrangement. We haven't compared notes yet, but we might do that one day. In terms of nutrient recycling, specifically very interested in cotton gin trash because it's rich in potassium, which is an essential nutrient, as you know, in most food or plant production systems. It also gives us pathogen control and energy offsetting of the drying of the ginning operation. We're looking at biochar and broiler sheds for animal health reasons and also nutrient retention, and then phosphorus recovery from biosolids, which again is where the funding from our point of view into the NIS Hub is going to give us some value. That work's been done with Bernadette and Peter, who presented yesterday. So that's us. But just want to say, very, very grateful for the opportunity to present. I encourage you all to continue your good work in research. You do some great basic research. I'd like to see a little bit more applied research in terms of what can we do, what's operably deliverable. Because without that, our research sort of hits a dead end. So I want to really encourage application of research. Thank you.
Good talk. Thank you so much. We'll take a couple of questions. He's also going to be in the panel this afternoon, but it's going to be a little bit of a different flavor. So, any questions on this? Yeah, let's take the opportunity while he's up here. All right, Catherine.
Hi, thanks, Durell. Really interesting stuff. I'm just wondering, that unit that you outlined that's treating the nutshells.
Yep.
Do you need to modify that for different feed materials, or is it the same unit just operated slightly differently for different feedstocks?
Yeah, the unit itself is the same. The front end feed management,
The front end feed management clearly is different for different feedstocks. So you've got varying density, particle size management, dust. So the material handling is the big deal. But the back end, so from the thermal oxidizer on, is critical, because without compliance, we don't have a license to operate. And that our challenge is to get the whole biochar producing world to follow that lead, because unfortunately that's not the case.
And in the Haiti and Vietnam examples, did you have the same setup, or was it a lower tech option for those use cases?
It was a lower tech option. Yeah, definitely, yeah. And it was coupled into existing kilns, so we were using the kiln as the oxidizer essentially. Yep. But we moved then from producing ash as an output from the rice hull combustion to producing biochar, which they then put into their fields. Yep.
I just had a quick question about the feasibility of smaller scale systems. I don't know if you've done any research on systems that are transportable, so moving to site rather than producing the biochar at one location and then transporting the biomass there, having it movable to different sites.
Yeah, definitely. That is an important point. Yeah, we don't want to be transporting the biomass. So you take the system to where the biomass source is. It's much cheaper to transport the biochar. You only got 1/5 of the mass to move. In terms of scale, we've had the smallest scale that seems to operate reliably is around about 200 kilos an hour. Any smaller than that, and we lose thermal inertia in the whole system. And the beauty about the gasification process versus some of the pyrolysis processes is its thermal energy efficiency. It's autothermal.
Just a quick one from me. As a chemical engineer, I'm curious about what might be the end product of PFAS in that gas combustion.
what's that?
The end product of PFAS combustion. So because there's going to be a little bit of PFAS in that feedstock, what might be the form it comes out as?
Yeah. So we've done quite a bit of PFAS study at the Logan Biosolids gasification plant. So you think about, there are two places that PFAS can emerge from that process. One is in the solid fraction, and then the other one is in the stack emission. In the solid fraction, the biochar, I don't know how many species of PFAS we looked at, Joe, hundreds, PFAS, PFOS, and not detectable. In the stack emission, a couple of species were still evident, but they were below the current threshold. And the regulator's most interested in the stack emission because it's dispersing, whereas the biochar is captured, contained. So we've got to make sure the stack emission's right. In terms of the output products, well, they're derived from petrochemicals, so, and then a few other things thrown in, largely carbon dioxide, carbon monoxide, nitrogen, into inert nitrogen.
I guess, yeah, it's the same for water recycling. Is really about what we don't know, and so like we might have to be really open-minded and looking for things that were not there in the first place that we might be forming. I
Yeah.
guess.
Well, PFAS isn't named a forever chemical for, if we want to reduce PFAS emissions, we've got to stop making them. It's that simple. So, we've got a better outcome than we currently have. It's not perfect, and I think that's the point in terms of adoption of research that's basic or pure research. We've got to apply that, and that comes with compromise. So we've got to accept those compromises.
Yeah, good point. So, thank you so much. We're kind of out of time, but we can catch him at the break and in the panel. So, well, before you are off the hook, we'd just like to present you with a little token of appreciation. Here you go. So, please join me in thanking